Hello everyone, my name is Flack and welcome to RRS Live 2020. So my research is in the optimization mechatronics for soft robotics under Dr. Vikas in the Department of Mechanical Engineering and in the Agile Robotics Lab. So most of the time when you think of robots, you probably think of something like this. And both of these are built with like either metal or rigid plastic. For my research, we took a different approach. We worked on soft robotics, so robots that are made out of soft, flexible materials. So this is the robot that I've been working with. It has 4 silicone limbs, and it has a bend sensor embedded in every limb. It also uses Bluetooth Low Energy to communicate, and all of the electronics are housed in this flexible hub. And the hub is made out of NinjaFlex, which is a 3D printer material that is flexible once it actually prints. Inside the hub, we have the printed circuit board, which connects all of the electronics together, as well as a motor for each limb, and each motor has a pulley with a motor collar on it. And so there's a fishing line that runs through each limb, and when the motor turns, the fishing line gets wound around the pulley, and that curls the limb, allowing it to move. This robot is specially designed so that it is modular, so that 6 of these robots can form into a ball, and this allows for different forms of locomotion. So like if just a regular robot has difficulty moving across sand, it can join with 5 others, form into a ball, and then roll across sand. So it allows it to adapt more easily to different environments. So this robot, the goal is that it can adapt to a variety of different environments. So that's why it being flexible is an advantage. So the regular robot is, if it's flat and not curled, it's about 2 inches by 17 inches, and then curled is about 3.5 by 10 inches. And so it can fit into tight spaces that a normal robot can't. And it does this with only 4 motors. So if you want to do this in a rigid robot, you would need a lot more. You would need some motors and all for locomotion, but some to actually change the size as well. So it's a lot simpler design. And so the goal is that we could use this in applications such as search and rescue, where you don't really know the terrain, but you need the robot to be able to adapt. So to actually control the robot, we have 2 different options right now. We have Bluetooth Low Energy with a phone app. So you can go ahead, connect to the robot, and then you can tell it to move forward, backward, left, or right. And it will also display data from the IMU and the bend sensor. So it can tell, so you can get real-time feedback on what the orientation of the robot is and how much each limb is curling. This data is also saved to a CSV file, so it can later be downloaded and analyzed. We also have the option to stay on. So basically, if you turn that little switch, then when you hit forward, it'll keep moving forward until you hit the button again to tell it to stop. We also have a serial computer app. And so this, if the robot is plugged into your computer, you can go ahead and communicate with it that way. And you can tell the robot if you want it to just flex a limb or if you want it to move in a certain direction. And you can also collect data this way from both the IMU and the bend sensors by clicking the collect button. And all that data is again saved to a CSV file that you can later analyze. So to actually make the robot move and all, we download all of the electronics onto the brain of the robot, which is the Arduino Nano 33 IoT. And this actually has the IMU built into it, so we can tell the orientation of the robot. It also has Bluetooth Low Energy built in as well. And this is where we control all the motors, tell them when to turn on and off. However, the pins of the Arduino can't actually provide the voltage necessary for the motors, and that's why we use a motor controller. And basically what that allows us to do is once we tell it to be on, the motor controller will take the 15 volts that the robot is given, and it will send that to the motors. Then, as I mentioned before, we have a bend sensor, which is the I2C sensor, and that is how we can tell how much each limb is actually curling. And then, of course, on the printed circuit board, we have plugs, so everything like the motors and the bend sensor that don't plug directly into the board can still connect. So to actually design the printed circuit board, I used Eagle. I made it so that it is two-sided. So on this design, you can see both the red and the blue traces. So the red is the bottom and the blue is the top. And that allows us to really get all of these parts closer together and have the electronics fit in a smaller space than they would otherwise. I also added the plugs for the I2C sensor, the bend sensor, so that we can collect data that way. Then I soldered, then we used the other mill to actually print out the traces, so leaving behind only what we wanted connected. And then soldered all of those together to actually get the circuit board. Then for the code to actually control it, I did what I would call intuitive programming. So looking at, okay, to get this to move forward, which limbs do I actually want to move? And that's how I came up with this. So first the back limbs flex, kind of lifting the back end of the robot up, and then the front start to flex, and then it starts to release the back limbs, and that kind of shifts it all forward. And then it releases the front limbs before it stops. Now, one thing I'd like to also point out in this code is the data delay function. So with this function, since we want it to we basically tell the motor, okay, we want you to be on, and then we want it to wait, but we still want to collect data during that time. But you can't multi-thread in Arduino. So what I did is made a function that would basically realize how much time has passed, and if there's enough time, collect data, and keep doing that until it actually reaches the delay that I want. So in the future, we want to add batteries to the robot because right now our robot has to be tethered to a voltage source. So we would like to get rid of that and have onboard batteries. We also want to have a Bluetooth Low Energy computer program and then optimize the movement of the robot, see if there's a way that we can make it move faster and better than what it's doing right now. We also want to expand our 4-limb design to 3 limbs or 5 limbs or however many we want. And with that, I'd like to take any questions. Sorry, I was having trouble hearing that. Dr. Sharp, I don't think your microphone is working.
Boy, can you hear me now?
Yes, I can.
Okay, all right, good. Sorry about that. Why are you using the BLE program to communicate with the soft robot?
So with Bluetooth Low Energy, oh, here we go. So it's got low power consumption. Because we'd like to have the batteries on board, we have to be very aware of how much power we're actually using. And BLE doesn't consume a lot. It's also already built into the Arduino Nano, so it's really easy to go ahead and already incorporate it for testing purposes so that we can do that wirelessly. Unfortunately, it does have a limited range, so in the future, we're thinking about maybe moving to LoRa, which stands for long range, and it's a method of like radio communication, and think about moving something that way so it could be more applicable in the future.
Why did you start with a four-limb design?
So we started with 4 limbs just to, well, so we wanted to make it so they could form a ball. And so the minimum to do that is 3 limbs. Also, the motor drivers we're using, they're dual motor drivers, so they can both drive 2 motors. So 4 limbs is something easy to start with. It's a nice smooth design. All of our electronics are very boxy, so it's a lot easier to fit them into the 4-limb design and then expand that in the future.
Were there other questions from other folks in the audience? Guess not. So with that, Chloe, wonderful job. Thank you very much and congratulations. Thank you. Keep up the good work.